I'm really excited to be here to talk to you all about building decentralized or peer-to-peer applications. I recently built one with a couple friends, and it was my first time doing so, and it was a real learning opportunity for me. I think like paradigm shift is a really dramatic word, but it definitely opened my eyes to different ways of building applications, which was cool. So I want to take you on that journey with me, a little bit of going from like not knowing very much at all about something to knowing a bit more. So the way we're going to do that is we're going to take this big concept of decentralization and kind of anchor it to a domain or example application that we're going to run through. And that application is a cloud file storage app. So if that term doesn't really make too much sense to you, just essentially think of a service like Dropbox, something where you can store files on the internet. Anyways, we're going to look at two main ways of building a cloud file storage app. And the app that I developed recently that was decentralized was one of these. So we're going to focus in on that one because that's the more mysterious one, the one that probably you're not so used to. So anyways, how this talk is going to break down is first we're going to talk about the what and the why. Like why would you even mess around with a decentralized thing? And then from there, the how is the kind of the bulk of the talk. We're going to cover trying to build some features, but essentially we're just going to be exploring the problems and possible solutions when you go about approaching a decentralized app. And finally, going to allude to this project that kind of inspired this talk. All right, so to get everyone on the same page, I first want to talk about the client-server model. In case you haven't heard of it, I'm just going to go over it briefly. This is not peer-to-peer or decentralized at all. This is the normal way of developing a web application. And if you've ever touched server-side code or even hit an API, if you've just done front-end stuff, you've worked under this paradigm. And yeah, just a browser going as a client, hitting a server, and delivering a response is that type of model. So anyway, now that that's we've got that covered, I want to talk about the client-server model in context within the context of cloud file storage. So most cloud file storage providers today use the client-server model to build their features and deliver the system that you're able to use to store files and download them later at your leisure. This is fine. It works pretty darn well, but they have a property in common that I didn't really think about before I worked on this project, which is that they're centralized. And that just means that this service requires central coordination and control in order to work. So you can just think of Dropbox's authentication feature. You don't worry about people accidentally running into your files on the internet. They have implemented an authentication system for you, and it's pretty darn reliable. This is a choice, though, for how you design your system. So let's consider what centralization does. Let's go through a list of pros and cons. First, it's kind of the familiar development model. You can probably work a bit faster in this way, but there may be some cons. So first, this is a quote from Mark Zuckerberg at a congressional hearing when asked if he could just freely share Facebook data about whoever with whoever. And the answer is kind of like essentially yes. So I guess we're supposed to trust them not to do that. But it might be the case that this is an instance where if you can do it, it's probably happened before, either accidentally or on purpose. Second, data security. There's kind of this essential problem where when you gather large amounts of useful information, valuable data, and centrally store it, people may and probably will come for it. You don't know if they're the government, hacker cats, ninjas, we just know that they're going to come. And finally, anonymity is a final con we're going to talk about. And so there's some great reasons to want to be anonymous on the internet, but there are also some not so great reasons. But that's not what this talk is about. What this talk is going to be about is we notice that these three cons, they all kind of have a trust component to them. So what that means is we are relying on some third party, like a service provider or our government, to be a good player and not abuse their access to our data. We don't own the keys to it, although that's not something you maybe think about every day. But what if we were more like Mulder and Scully? What if we trusted no one? What would a trustless system look like? So it might look decentralized. That could be one approach. And this looks pretty promising. There's like extra lines everywhere. But how does that actually address our trust issue? We're gonna start comparing centralized and decentralized systems to try and explore that question. So the first thing is these kind of decentralized systems visualized on the right, they don't have any central authority. And when we remove that central authority, we effectively transition from the client-server model to something where we have peers and peers and other peers connecting on a network. And at a more practical level, we no longer are dealing with clients and one or more servers. We're dealing with these client-server nodes that are autonomous. So we'll explore that a little bit more. First, just a terminology note. I may use like node and peer and device interchangeably, but they all can kind of refer to one of two things, either a personal device like a laptop or a remote server. It could be by DigitalOcean or Amazon or whoever. So it's kind of like complicated to figure out where to start. You know, we have this decentralized idea, but where do we go from there? So a good place to start is maybe the simplest cloud file storage system we can make. Let's just try building something, see what happens. So here's a definition that I completely made up, full disclosure, about what the most basic cloud file storage system might be. It might be something where you can upload your file to the cloud, delete your own file locally, but still be able to get that same file later. And because we're talking about decentralized systems, we're going to add in a final requirement, is that it's peers only. If we had to put up a sign and say no servers, no clients. Okay. So now that we know where to start building, we're going to start with this upload process. And we're going to walk through each of these steps in the following slides. But the central idea right now is we're trying to get away from an owner node to transfer a file to a host node. Now this may actually kind of look like a centralized system, right? It's just two entities on a network, but in fact they're peers. So maybe another way, to describe it, they're equal and autonomous. Neither of them have extra privileges over the other. Another way of maybe looking at it is this is node 1 on the left, node 2 on the right. We can completely switch their roles because they're role flexible. A client-server node is the same thing as like a host owner node. We could also describe it that way. That's maybe more reflective of our domain. This is a node meetup, so I maybe should have used triple equals, but it's all right. So let's get started. The host creates a TCP server. There's a callback that has some logic in it that we'll address later. And then on the owner side, they're also going to create a TCP server and afterwards connect to the host. They do so by connecting on the same port as the host, and whereas before they connected on their own port. Finally, once that's done, they're able to send messages and data over to the other node. This host that's already created their server is now, once it receives that data event, can check the message type and download the file locally. So we've done it. We've made a super basic system, but it's probably not that good. It's like a good worst cloud storage system because, if it's not super clear right now, this is a really bad system for storing your files reliably, and we'll go over that shortly. So this system is highly likely to fail. If there's anything happens with the host, our file is toast, you could say. So what do we do about that? What we do is we need to expect failure with our system. And we can't just ruminate on the fact that it's going to fail. We need to design the system so that it can fail effectively and heal itself. Let's talk about a metaphor if that sounded like mumbo jumbo. So this is Allies have, it's World War II, the Allies have landed in Europe. This looks like a really complex operation, right? They got freaking Zeppelins and stuff. So there's a lot of resources, a lot of planning, a lot of control. So it could be like a large system. Maybe something, we could think of it like an internet giant with their application that provides services for millions of people. Sometimes people wonder, why does Facebook have so many engineers? Because a big system requires a lot of work. But the thing I want to talk about is some systems don't require as much central coordination. Here's an image of paratroopers maybe in preparation for the Allied landing in Europe, landing behind enemy lines. It's chaos, right? They're landing everywhere. So what they did is everyone knew their appropriate mission, and they were able to form their groups themselves and go and execute independently. They didn't need central control. So let's think about let's take these ideas and think about how we could use them to make a better cloud file storage that was still decentralized, but maybe more feature comparable with something like Dropbox. We'd need to essentially solve these 4 problems that we haven't yet at all. We actually don't really have time to solve them, but let's solve this one at least. It's got some interesting sub-problems, and yeah, I think it'll be a good ride. So let's talk about how to ensure file privacy. It's a pretty simple concept. Only you should be able to see your files. Only you should be able to update or delete them if you wish. So let's look at how the two systems approach, the two central development models approach this type of challenge. One is probably pretty familiar to you. It's authentication. If we have different clients connecting to a central server and they're exchanging files, each client maintains access to its own separate file. They don't kind of get in the mix. However, that's completely different in a decentralized system. In a decentralized system, everyone has access to everyone else's files potentially. So what our goal should be is to make physical access, for lack of a better term, to a file useless. Instead, except to the correct party. So we'll explore how to do that. Here are this two-layered approach that we're going to be using to do this. And file sharding may be a little less familiar to you, but we'll get to it shortly. First, we'll talk about encryption. If an owner does not have their own key, they need to generate one. And once they have generated one, then they're able to encrypt their files. Now we have effectively client-side encryption, and because it happens before the file goes over the wire, and we're only dealing with one key, so it's symmetric encryption. So our upload process is better, and our download process is safer as well. We have hosts that can't read files that they've been given physically. That's very different from a centralized system. You should never get access to a file you don't have access to, have been given access to. But the owners are still able to read them. Next, we want to think about extra failure, right? Because it's kind of risky to give files to random strangers. So what if a host actually gets access to our key? How do we respond to that potential eventuality? Well, file sharding is going to be our answer to that. First, it starts off by splitting up a file into smaller pieces, and then we give each file a unique name based on the hash of the contents of that shard. From there, we have this new upload process, and it's a bit safer, I guess. The host now has a couple pieces of the file to deal with. We've also made our own lives pretty difficult. We've now can't guarantee the order of the content when we pull it back down. We've disassociated the name from the content itself. So if we dealt with multiple files, it would be completely unfeasible. So what we're going to have to do is think of a way to organize that better. We're going to do that with a thing called manifest files. So manifest files are going to help us retain order of our shards and also keep the file name and the shards in order and keep track of them as well. Here we can see just a simple JSON-like object in a file, and we don't need to worry about, we can do this without databases, which is nice. So we're back still to our problem of keeping these files extra safe, and the central issue is we have all of our eggs in one basket. All pieces of a file are being stored by one host. Additionally, what if we give like a movie file to this host? Then they don't want to offer that much space, or they don't even have that much space. That's not even going to work. So what we have to do is spread out the storage burden somehow. That's going to complicate our lives more, but it's going to make our system way more effective. So let's think about how would we do that. Where are we going to send our shards? Do we send them all to one node? Do we send a couple? Like, how do we do this? It's not, yeah, those were going to be a problem for our system. So we're still trying to think of a way that we can distribute the load of files across multiple nodes. And say we have a list, we have like a bunch of shards and we have a bunch of nodes. maybe we could just have a list and like iterate through that list. How would that work? So let's check out this master list example. Seems okay. We have 4 nodes and 4 shards. Just boom, boom, boom. Send them up there. You could just do the reverse to get them back down, right? But we should think about some properties of the system. One is that all of our nodes are autonomous and equal, so they all need their own node lists. So we're not just dealing with one like master node list. We're dealing with n master node lists. So that's getting to be a bit of a pain. A second curveball that we should expect to happen is as our system scales from, like this is 4, what if we had 4 million or 4 billion nodes? Those would create really onerous data storage burdens on each of the nodes that wanted to participate in the system and would be a nightmare to update. So that system's not going to work. So let's think of another system. But first, let's break down this problem a bit. A more essential question might be, where do we store one shard? Which host should it go? We're trying to establish that relationship. And in order to do that, we could also think about the opposite question. Once it's uploaded, we also need to be able to understand how we retrieve that shard. So if we think about real-world examples, if only there was a system that we could access arbitrary resources over long distances, like the internet. That might do that. It needs to do it reliably. We need to be able to access the same resource every time we go there. So how does that work? That might be something worth exploring. There might be some sort of coordination or routing going on. So let's check out this classic interview question. What happens when you go to google.com? My friend told me that if you say something like, well, there's just like wizardry and magic going on, and then you get to Google, the interview doesn't go so well. But maybe you know something a bit more. Maybe you know about DNS. And hey, like you just throw in a domain name, spits back out an IP address. It's an instant lookup thing, right? But actually, it's not quite that simple because the DNS, it's not a single centralized database. It's distributed across zones. And each of those zones, there's one or more domains. And each zone is managed by a name server. But anyways, DNS examples aside, this is kind of interesting, right? There's a distribution of data across a tree. So how does DNS deal with that? Seems like a similar problem that we're facing. Well, when they do lookups, they do this kind of like iterative lookup thing, which is kind of interesting. They, in a kind of simplified example, will always go to the root server, the org name server, and so on. And they do this based on a hierarchical structure. Now, our system doesn't have any inherent hierarchy to it, but this is still interesting, this iterative lookup idea. And also this distribution of data. Maybe we can make use of that. But let's think about the properties of our system. What's unique that we have if we don't have hierarchies? What we do have are IDs, or shards have been given IDs. That's about as much as we have to work with right now. But IDs are pretty cheap, right? So let's give the nodes IDs as well, right? But how does that help us build zones? How does that allow us to distribute data burdens across a network? Well, another metaphor. We have 2 people on either sides of the US, but we don't have any centralized data or centralized tools in order to reach them. Like we don't have Google. We don't have even phone books, say. But we do, let's give them phones. What would you do if you needed to find someone in New York? You might talk to your friends. You might, but maybe you don't have any friends in New York. Who do you decide to talk to? We need some sort of heuristic or metric in order to choose the best person, the most likely. Well, you can't call all of your friends and ask about this one random dude. They might get weirded out. But you can maybe take the time to ask one person. So let's actually just check that the person most eastward in hopes that we eventually get to someone in New York and then someone else in New York City, and then that 6 degrees of Kevin Bacon separation thing will kick in and we'll get to him eventually. We can't really guarantee the minimum number of hops, but we're going to get closer and closer. So we're using a geographic metric for closeness. So let's think about a closeness metric for IDs. Our closeness metric is going to be logical closeness. So how we answer the question of where do we send a shard and to which node? So we're going to send the shard to the closest node's ID to the original shard's ID. Maybe that didn't make too much sense, but the answer more specifically is we're going to take the XOR distance of each node's ID. Now, if your bit manipulation skills are a bit rusty, here's like some examples. It's not super important. There's like mathematical definitions and bit definitions, but this is the one I use. Like, if we're looking at two values, say ones and zeros, these two rules on the right are going to determine when we get a 1 back. Anyway, quick example with some simplified IDs. So these are more like hexadecimal values. But here's just some binary ones that are a bit simpler. The first one on the left is only one significant digit and a 1-bit difference, so it's at a distance of 1. This one is at the third significant digit, so 100. In binary, in our real number system is 4, so that's a distance of 4. So that's interesting, but we're going to need a lot more to get this whole system working. This is an interesting idea, but we're not there yet at all. So I'm just going to skip to what we ended up using. We used a data structure and protocol specification called Kademlia. It's a flavor of distributed hash table, and it's used to power various decentralized applications that are in use today. We did not want to code this thing entirely ourselves. There are pre-existing libraries, and there's actually a really great one in Node.js called Cadence. If this is something interesting to you, I definitely encourage you to check it out. So next, we are going to look a little bit more at what Kademlia does. For each node in the network, it has a routing table, which is a tree of buckets within a certain bit space. And each bucket contains, or otherwise referred to as K bucket, holds K number of contacts. These are interesting details, but there's a lot more questions about how would this system work. And it would take, honestly, a lot of time to explain. So to answer these questions, I'm not going to do it. We're just going to black box this for now and just like hop over that rabbit hole. And yeah, but let's return to our system. We've implemented Kademlia. It's going pretty great. And here we've got the first benefit. We have smaller lists or buckets or whatever we want to call them. This was the master list idea before. And we now, instead of having n size lists, we have log n. So that's a big improvement. And this has allowed us to also distribute storage across the network, which has increased its flexibility. And that, in turn, has allowed us to store large files on the network. So uploading a movie file is now at least feasibly possible, where it was previously going to be very, very unreliable. Excuse me. So we've come a long way from our super simple, super ineffective system that we created earlier. And I want to take a brief detour from the building to talk about the kind of the project that inspired it. Myself and a couple other friends made something called Layer, and we built similar feature set to what we've talked about today, but in terms of the file ownership. But we also built other features as well that unfortunately I don't think we're going to have time to talk about today, but they were definitely very interesting. This is us. We're a distributed team. We first met through an online learn to code program a while ago and kept in touch. And I was previously in Portland, and Tanner's now in New York. Flo is here in the Bay. So we could do a quick demo of, it's not the best quality, but what's happening here is the person uploading it, Tanner, is using a CLI to upload a JPEG to the network, and it is generating shards locally, and also each of these shards is encrypted, and there's also an entire encrypted file. And here, just to demonstrate it's working, the local files are being deleted, and we're again using the CLI, and in this case the list or the L flag to see all of the manifest files that we've generated. Then we use the manifest file to pull it back down locally again. And we have the file again, and it works. All right. There's also, oh, did that skip the thing? Here, we'll just do this patching one real quick. This video is too fast, but what's happening is this person has executed a patch command, and an audit has failed. So this file did not have enough redundancy. I actually kind of regret showing this video because we didn't really get to those topics yet. But it proved to you I wasn't just making it up. But if you really want more proof, more understanding of what we did, I really encourage you to check out this blog post that we, or more like project overview that we did, that goes in detail of how we built the different features in our thought processes. It kind of mirrors the style of this talk. So if you found that interesting, you can definitely check that out. And finally, I also wanted to mention that there are some links that you might find useful. We did kind of skip over a lot of details of distributed or decentralized systems and Kademlia. Finally, I'm looking for my next team. So you can find more information about me here, or you can talk to me in person about decentralized systems or anything at all. So thanks for listening and dealing with the difficulties.
Who's got a question?
I have a question.
Shoot.
She had her hand up.
Okay.
Hi, yeah.
So by the network, you mean the blockchain network,
The network.
like a decentralized system on the blockchain network?
So there's,
Can you repeat the question?
yeah, so the question was, by the network, did I mean the blockchain network? So there's a couple different functionalities going on here. One is just the upload and download of files. That's just, when I use the word network in that context, I just mean the internet. Like we are able to create, in our case, just TCP servers and then have files be transported back and forth across participating nodes on the network. You may have seen something later on where I threw up in the like kind of incentives part of the project that there was, we wanted to make it so that, you know, this is not just like a free rider system, like maybe there could be some underpinning technology that makes people want to participate and offer up space or not. And in that case, we did hook that up to a test net, or maybe like a test wallet using Stellar. So that had some crypto tie-ins there, but it was completely, you know, it's just test net stuff.
I see. So it's only available to participating members, like that.
Yeah, this isn't like a hosted service you can use today. If you really want to get rid of Dropbox, you'd have to like make your own community around it. And if this type of storage is something interesting to you, there are two companies, at least that I know of, that I neglected to mention, that were kind of inspirations for this project. One is called Storage, spelled STORJ, and they have a great white paper that we referenced when building a lot of our features. A second one is called Filecoin, and yeah, it's decentralized cloud file storage, kind of similar to the system we talked about today. Yeah. Sure.
My question is, you've taken the user's data and you distribute it over a bunch of networks, but the code that actually controls everything is being built by one entity, which is your company. So in a way, it's still, there's that sense of centralization, and people have to trust the company who writes the code and controls it to trust.
So I neglected to do one thing, which is leave out a keyword. This is a completely experimental project. Only us, when we're messing around with the system, are using this in a file storage-y way. So yeah, it's. I agree with you that when people are making decentralized systems, you probably need to check in on that company as well. But that wasn't an issue we faced here. Yeah.
Are you using open source, just to kind of piggyback off his question, are you using the idea that it's open source, that you don't control the code, or would you close it? Because I would feel comfortable using open source.
Yeah. So in the blog post, we actually say, like, this is really interesting. It's an experimental project we've been working on. Would encourage. It's up on GitHub and open source. And if you want to contribute to it, that's great. If you want to, do whatever you want with it because it's open source, that's also great. But we probably wouldn't recommend it as a viable, stable way to store very important personal files for you right now. Because it's, at any given time, like right now, there are 0 people supporting it. You need sort of a critical mass to get something like this working. So if you have a lot of friends with a lot of servers lying around, might be able to work something out. That'd definitely be fun. But yeah, right now the closed source thing, I would kind of recommend asking the people that are, running this as a professional service where they want to ask for serious money from people in the future, how they would approach that type of issue. Yeah.
How does this compare to BitTorrent Drive?
So BitTorrent, BitTorrent Drive.
So
I was going to
Drive
answer one way, but
system
then,
that basically does the same thing.
Yeah, I'm completely unfamiliar with that system, but if I had to guess, based on their previous work and also use of things like Decentralized, decentralized systems, it might do something pretty similar. Those other companies are getting some traction. Yeah.
Yeah. Two-thirds of the world population is disconnected.
Yeah.
So actually, blockchain is one of the ways to connect them.
Yeah, I'm not an expert on blockchain at all. And I actually did the least amount of work on the blockchain stuff for this project. But there are a number of other pros and cons to this type of system that I wasn't able to talk about today because, there's just so much to talk about. But one of them is that if you make a decentralized, I think IPFS is talking about this. They're a company that's also doing the Filecoin thing, and they want to make the decentralized internet. So instead of we kind of take for granted that a lot of our services that we enjoy are, say, like based in San Francisco. We have really low latency costs because we're located very close to these valuable services. People living in other countries that are very far away are not necessarily so fortunate. So they're kind of exploring how to, maybe improve that latency story for people in more rural regions. And I think actually this technology might have some applications there as well. If you're relying on storage being close to you, like we do here, to be very fast, that's not a luxury that people in other countries can necessarily enjoy. So there might be some applications there as well.
Yeah. Decentralization needs some education. If you have 2/3 of the world population is illiterate, doesn't understand the codes and all that stuff. So how do you connect to this 2/3 of the population of the world which is disconnected?
Yeah, that's a great question. Just a simple engineer, so I don't have all the answers.
How do you solve the world's problems, sir? I demand an answer.
We get right back. Yeah. Did you have something?
No, I think that was our last question.
Cool.
If you want to ask him some more, please come up to him at the end. We're going to have data here soon, and I'm going to have to